All right, howdy guys. This is kind of picking up where we left off on Sunday. So Sunday I posted the beginning of section 9.5 lecture because I wanted you to be prepared for your lab on Tuesday. So if you need a refresher, make sure you go back and look at those videos and slides for section 9.5. This is going to continue with section 9.5, but I'm not going to redo the stuff that I already did. So if you want to watch the videos about concentrations in concentrations in molarity and how to calculate moles from a concentration, or how to calculate concentration from a given mass and volume, then you'll have to rewatch those videos, or at least check the book and the slides, um, or watch the videos for the first time if you didn't watch them yet, since I said they weren't necessarily necessary. Um, so picking up where we left off, we are making some more solutions, and sometimes we want to have multiple dilutions of the same solution. And when we do this, when we make multiple dilutions of the same solution, this is called serial dilution. So we are diluting a series of solutions. And when we make serial dilutions, so that process means that we start with a pretty high concentration solution, and we make one dilution by adding a precise volume of water to a precise volume of our solution, and that the product of that process is our first dilute solution. So now we have two solutions, the really concentrated one and one that is slightly less concentrated. So after that, we repeat the process, but instead of starting with our high concentration solution, we start with our newly created diluted solution. And we make an even more dilute solution by adding a precise volume of water to a precise volume of the diluted solution. And we continue this until we have the desired number of dilutions or solutions. So for example, this is a picture from your book, and I think it's pretty nice because potassium permanganate has is a pretty pink purple color depending on the concentration. So this is a serial dilution of potassium permanganate. That's what this looks like. You will be doing this in Chem 120, but not in Chem 119 lab. So keep this in mind for when you get to Chem 120 lab. But just to go off of this a little bit, the first solution here is, so this dark solution, it's almost black looking, is 0.0400 molar. The next one is a tenth of that. So we diluted it by adding, say, 10 milliliters to our volumetric flask, and then adding 90 milliliters of water, so that we have 100 milliliters of solution with only 10 milliliters from the original solution, so that our new concentration is 0.00400 molar. And then the same thing was done for these other two dilutions. So here we added 10 milliliters of, okay, just draw my little arrows. We added 10 milliliters of this solution number 2 to our empty volumetric flask, and then we diluted it up to 100. We added 90 milliliters of water to dilute it up to 100 mils total. So we have 100 milliliters of our solution now, but only 10 of it came from solution number 2. So this is now a diluted solution that is 1/10 the concentration of what we had before. So now this one would be 0.0004 molar, and 00 for our sig figs. And then we did it one more time, where we added 10 mils of solution number 3 to our volumetric flask and diluted it up to 100 milliliters. So we added 90 mils of water so that we could get 100 mils total, but only 10 of it came from solution number 3. So if you think about it, technically we had 10 mils of solution number 1 that went into solution number 2. So 10 mils of that went into solution number 3, which means that only 1 mil of the original solution ended up in solution number 3. So it's 100, it's 1/100th of the concentration of solution number 1. And by the time we get to solution number 4, we added 10 mils from solution number 3, which only contained 1 mil from our original solution, technically. So when we did that, now we only have 0.1 milliliter from our original solution in this 4th dilution, in solution number 4. So there's only 1 mil from number 1 in there. Or sorry, 0.1 mil from number 1 in there. So it is 1,000th of the concentration of what we started with. We add a 0 every time because we're diluting 10 mils to 100 mils every time. And you can see, so you can physically see the decreasing concentration because our color intensity is fading. So we had a really dark, almost black looking color when we started, and it faded to a purple when we made solution number 2, so it's less concentrated. And then it faded to a pinkish looking solution, or magenta, when we went to solution number 3. So it's even less concentrated or more dilute. And our last one is just a little hint of pink. So that color fading towards colorless means that our concentration is decreasing towards, a concentration of 0, which is just water. No more potassium permanganate in our solution. So as the color decreases towards colorless, your concentration is decreasing towards 0. All right, so, oops. So we're going to talk a little bit about this process and why we would want to do a serial dilution. So there are probably more than one reason, but the main reason I'm going to talk to you about is that we want to do a serial dilution of a known concentration of something because we want to be able to find out an unknown concentration from our random collected sample. So how would we do that? So what we do is we use something called Beer's law. So Beer's law relates the absorbance of light by a solution to the concentration of the species in the solution. So what does that mean? Let's start from the beginning. Your textbook goes through this a little bit, and let's think about there being a light source here. So this is like a light bulb. Don't judge my drawing of a light bulb. So there is a light source. Usually it's like a laser, not a light bulb, but this light source is shining on our sample with an intensity of I sub 0, or I naught, and that is the incident light intensity. So that's what we start with. When that light goes through our sample's in like a little container called a cuvette. When the light goes through that sample, it comes out on the other side, and it's probably a little bit different. So the transmitted light intensity is probably at least a little smaller than the intensity that we started with, I would say. So there's probably something in our solution that is blocking some of that light or absorbing some of that light so that the light that comes out is a lower intensity. And we call that the transmittance of the solution. So the transmittance is the relationship between the incident light intensity and the transmitted light intensity. So basically the ratio of what came out to what went in. And we can write that as a percentage if we want to. But the more common way that we would report it is actually not the transmittance, but the absorbance. So the transmittance kind of tells us about the light, but the absorbance, which is related, tells us about our solution. So we'll put a little T here, sorry, and a little A here, that's T. So instead of talking about the transmittance, we like to talk about the absorbance. So basically, whatever is in our sample is absorbing light, which is why the light that comes out is a lower intensity than the light that went in. So that absorbance is related to the light that comes out by this equation, negative log of the transmittance. So we can't actually measure we can't physically measure how much light is absorbed by our solution. We can only physically measure the change in intensity of this light. So there's a little detector over here that is not in this picture. But we don't really care about the transmittance, we care about the absorbance. So we measure the transmittance and then we convert it into an absorbance so that we can learn something about our solution. And there's a couple other variables involved here. The concentration, obviously, is what we're trying to talk about. I said absorbance is related to concentration, and I'm getting there. There's another variable as well, which is the path length. So it depends on how wide our cuvette is, how far across our solution the light has to go. So that's included in our calculation. So the calculation that relates absorbance to concentration is called Beer's law, and it is this down here. So A, which is absorbance, is equal to epsilon, which is the molar absorptivity of the solution, times the path length times the concentration. So A, I like to say ABC. I kind of omit the epsilon from my acronym so that I can remember ABC better, but Beer's law is absorbance is equal to the molar absorptivity times the path length times the concentration. And the molar absorptivity is kind of a constant for different chemical substances. Not quite. It's described a little bit more in your book, but you don't need to worry too much about it for now. And getting back to our serial dilution story, we perform serial dilutions in order to make a calibration curve using solutions of known concentrations. So this is what a calibration curve looks like. And each one of these points corresponds to the intensity of one of our solutions. So for example, these three solutions are made via serial dilution. We dilute the first one by half. So we add half of our solution and half water to get to solution number 2. This is 1, this is 2, and then we do it again. We take half of solution number 2 and dilute it with half water. So, and then we get a 50% dilution of that. So note that 50% and 50% do not add together. This is a multiplication. We take 50% of the first one and 50% of the second one ends up being 0.25, or sorry, it ends up being 25% of the first one, if we want to look at it that way. So number 3 is 25% of the first one, number 2 is 50% of the first one. And if we keep going, we are not gonna get to 0 unless you do a whole lot of serial dilutions. Technically, you'll never get to 0, but you might get close enough that it doesn't enter. Because again, we are multiplying, not adding, subtracting. So every time we get half as concentrated as before, but not 0. Anywho, these points on our calibration curve correspond to our different dilutions. The most concentrated one is going to be the first one. So the highest concentrations on the x-axis, has the highest absorbance on the y-axis. This is a direct relationship between A and C. So as concentration goes up, absorption goes up. As concentration goes down, absorption goes down. So these are our increasingly dilute solutions. So decreasing concentration and decreasing absorption as we go this way. And so from our calibration curve, we can demonstrate Beer's law. We can see how well our trend line fits this relationship. It should fit very well. It should be a direct relationship. So the linear trend line should work pretty well for us. And we can determine the unknown concentration of a sample using its absorbance. So we have no idea what the concentration of a sample is. Say we're taking like a, I don't know, water sample from somewhere, and we want to see the concentration of some ion in this water sample, but we don't know what it is. We can find its absorbance. We just shine some light on it and see what happens. As long as we use light of the same wavelength that we used for our calibration curve, that concentration is going to be somewhere on this curve. So your book pointed out with these red lines. So say you wanted to find the concentration of your unknown sample, and you test it, and your unknown sample has an absorbance of about 0.8. Then you just, put that along your line. And how do we do that? We do that by plugging it in to the trend line equation. And the trend line equation, since this is a direct relationship, is going to look something like y equals mx plus b. So in an ideal world, there is no b in Beer's law. See, there's no constant being added in Beer's law. But in the real world, you're probably going to get a y-intercept of something. And because we're not perfect, our samples aren't perfect. So that will be in there most likely, but it doesn't really correspond to anything physical other than error in your measurements. But y is corresponding to A, x is corresponding to C, C, and then m, the slope, is corresponding to these two constants, basically, for our solution, the molar absorptivity and the path length. So you can calculate any one of these things. I don't know why you would want to calculate the path length, because you should know what it is, but you could, I guess, using this equation. But usually we use this to find the concentration of some unknown sample by measuring its absorbance and plugging it in to our trend line equation that looks like y equals mx plus b. Alrighty, cool. So now let's talk about the pH scale. Sorry, that was really long discussion of serial dilutions, but they are super useful. That's like one of the most useful techniques in chemistry that you're going to learn in general chemistry lab. Anywho, now let's talk about the pH scale. Aqueous protons, which we write as H plus ions, that's a proton, because hydrogen without an electron just has one proton and doesn't have any neutrons. So those aqueous protons do not exist as isolated species in solution. They are hydrated just like every other aqueous ion we talked about in section 9.1. So we sometimes write our hydrated ions, or hydrated protons, as the hydronium ion instead. So just to let you know, you might see H plus or H3O plus in chemical equations and calculations from here on out, but they mean the same thing fundamentally. Of course, you got to balance your equation a little bit differently if you're using the two different kinds. But other than that, they mean the same thing. They mean that there are protons in our solution. And any proton in an aqueous solution ends up actually being more like that. So this is just your little equation of what's the more realistic way of writing when HF, your weak acid, reacts with water. Anyway, so just be on the lookout. If you see H3O plus, you can just think of it as H plus if that is easier for you. They are interchangeable. To describe the acidity of a solution, we use the pH scale, which is based on base 10 logarithm of the proton or hydronium ion molar concentration. So either one, they're interchangeable, like I said. So you might see it as pH equals minus log of a hydronium ion concentration or minus log of hydrogen plus concentration or proton concentration. So these brackets that you see here, we translate that as the concentration of usually ions, but sometimes just solutions. So if you see brackets, that means we're talking about concentrations. So the base 10 logarithm. So this is where our sig figs with logarithms are going to come in, and it's going to be lots of fun. You thought maybe we would never see logarithms in this class, but we will a little bit. All right, so using this equation, we can see that pure water, which has a proton concentration of 1.0 times 10 to the negative 7th molar at 25 C, has a pH of 7. So we plug this number in. You should do it right now. Plug it into your calculator and see, make sure you get 7. So pH is equal to the negative log of that concentration. So type in your calculator negative log, and in the parentheses that come up, it'll be 1.0 times 10 to the negative 7th, or 1.0 e negative 7. And you should get 7. So remember, there is a negative sign in front of here, so you might actually get negative 7 if you don't include that negative sign, which makes it positive. So most of your calculators, I imagine, just have a log button, and you don't need to specifically seek out log 10. But if for some reason your calculator is giving you weird errors or not giving you 7, then you're probably plugging something in wrong, or your calculator is extra special, and you should ask me about how to fix the problem. And another note here, pH is unitless. So there are no units on pH, which can be a good thing, can be a bad thing for your calculations, because sometimes units are great for helping you solve calculations, but I know you guys don't like to write them. Anyway, so neutral solutions like water have a pH equal to 7. So neutral is pH 7. Acids have a pH of less than 7, and bases have a pH of greater than 7. So a pH of like 1 is a pretty strong acid, and a pH of 14 is a super strong base. And we can look at this nice scale here. The hydronium ion or proton concentration is on the left, and it's plugged into our equation here in the middle, and our answer from that equation, so our pH, is over here on the right. So you can plug all of these in to test it to make sure that you're getting the right answer. So maybe you should, if you're worried, plug them all in. So it's just basically that exponent, that's the important part, that gets you to this value. So really low concentrations of hydronium ion would be down here. So really low concentrations. So 1 times 10 to the negative 14th, it's a really teeny tiny number. So that's a really low concentration of protons or hydronium ions, whichever way you like to think about it. So that really low concentration means we have a high pH, and that's a base. So a really low concentration means we don't have a lot of things that are giving off protons. That's our definition of an acid. It's something that dissociates into protons or something that creates protons when it reacts with water. We don't have that happening very much in a base, so a base has a high pH. Whereas an acid, on the other hand, this is a really big number, a really big concentration of protons slash the hydronium ions. So it might not seem like a really big number, but 0.1 is a huge number if you're considering that these protons are super tiny and, you know, water doesn't have that many of them. So when we have a concentration of 0.1 molar, that's super high. So we have a lot of hydronium or proton ions in solution. So that means that we have a lot of things that are dissociating into protons. Strong acids do that. We have a lot of things that are reacting with water to produce protons. Strong acids do that. And we have a super low pH for strong acids. So the scale of pH is only 1 to 14. So super low and super high is kind of a relative term, but it makes a little more sense when you look at the actual concentrations. What I mean by super low and super high. Cool. So we can also go backwards and use a sample with a known pH to calculate the proton slash hydronium ion concentration of the sample. So sometimes we know what the pH is, and we want to know what the proton concentration is to, do some calculations with that concentration, because that concentration gets us to a number of moles, which we put into our stoichiometry problem to solve for different reactions to see how much is produced or how much we started with, whatever. Sometimes we don't know the concentration and we only know the pH. So let's practice. We're going to use this equation. So 10 to the negative pH, so 10 to the exponent, is how you undo a logarithm. So they are, opposites of each other. Just like x and 1 over x are opposites of each other. They like undo each other. This is how you undo a log. You do 10 to the minus pH. So if we want to calculate the hydronium ion concentration, I'm just going to write it like this. This is our concentration. Again, it's in brackets. That's how we know it's a concentration. Oops, there's a plus there. Is going to be equal to 10 to the minus pH. Our pH is 5.2. So 10 to the minus 5.2, I plug that into my calculator. Like your book says, most calculators will have 10 to the x power as the second function of the log button. So if you look at your log button on your calculator and you look at the little number that's written above it on like the actual calculator instead of on the button, that is where you should see 10 to the x. So you hit the second button and then the log button, and that gets you the function 10 to the x. So I'm going to hit that now, and that plugs it in. Let me just show you this. So that's what it looks like. There's my button, see log, and then right above it on the actual calculator, not printed on a button, but printed on the actual calculator, is 10 to the x. And I pressed second log button, so my second button and then log, and I got this. This is what it shows me so far. And now I'm going to plug in negative 5.2 and see what happens. Okay, so I did that and I got 0.0000631. So I'm going to write that out. So your calculator, if you have it set up properly, which I apparently don't, might be in scientific notation already, but mine isn't. So I've got 1, 2, 3, 4, 5 zeros and 6, 3, 1. Okay, so what is this concentration in scientific notation? 1, 2, 3, 4, 5, 6. So 6.31 times 10 to the negative 6 molar. That's my concentration of hydronium ion. And if we want to be particular about our sig figs, so based on what your book says and the rules for sig figs. When we do the logarithm of a number with 2 sig figs, it gives us 2 decimal places. So it's not about the sig figs, it's about the decimal places. 2 sig figs plugged into a log gives us 2 decimal places with our answer. But when we're going backwards, we have the opposite problem. So 2 decimal places on our number that we plug into the 10 minus pH, 10 to the minus pH equation. So we have 2 decimal places here. So we're going to go backwards with that rule. 2 decimal places is going to tell us that we should only have 2 sig figs in our answer. So our correct answer should be 6.3 times 10 to the negative 6 molar. Sig figs are harder with logs and anti-logs, I'm going to call it. But you guys can do it. It's just remember 1/2 of the rule and you'll remember, and then you'll be able to hopefully figure out the reverse of the rule like I just did to show that get the right sig figs for both types of calculations. All right, and then this was on the slides from Sunday, but I want to just kind of emphasize some things here again. The concentration of an ionic compound in solution and the ionic compound formula can be used to determine the concentration of specific ions in a solution. So your book kind of phrases this as solution stoichiometry. I never would have thought of it that way, but I'm going to rephrase it that way because that's what your book does, and I want to be consistent. So we have calcium chloride, aqueous solution, and it is dissociating. It is an ionic compound. It's it's soluble, which is why it says it's aqueous. So it dissociates 100% into calcium ions and chloride ions. And this is important to note that we look at our ionic formula, and that actually tells us there should be 2 chloride ions, sorry. So the concentration, if we have 0.344 molar, that's our concentration for calcium chloride. It's a 1-to-1 reaction with dissociation. Not really a reaction, but we're going to call it a reaction for now because we have a chemical equation. Anyway, it's a 1-to-1 dissociation. So that means we're going to end up with 0.344 molar calcium 2+. But there's a 2 here. So if we have 0.344 molar calcium chloride, we can use stoichiometry to find out that we use our mole ratios, there's 1 mole of calcium chloride for every 2 moles of chloride ion. So the concentration of chloride ion should be twice as much. It should be 0.688 molar. So the concentration of your ionic compound is not necessarily the same as the concentration of its constituent ions. That depends on the ionic formula, which, when it is fully dissociated, produces as many of that ion as are shown in the subscript. So you can see that kind of pictorially here in this beaker. There are 4 calcium ions and there are 8 chloride ions. There's twice as many. So we have twice as much concentration. Our concentration is twice as big. So I just wanted to emphasize that for you because that wasn't super clear before, maybe, or at least it wasn't phrased the same way that it is in your textbook. So final problem here. You guys can pause and take the time to solve it yourself, but I'm just going to do it real quick. All right, so this combines pretty much everything in this section other than pH for us in a nice little problem to sum up everything. So we've got 22.5 grams of cobalt sulfate, and we want to make a solution out of it. So we are going to add that solid to our volumetric flask and then dilute it to the mark. So we dilute it so that it is exactly 250 milliliter solution when we're done. So we want to find the concentration in moles per liter, molarity of the solution, and the ions in the solution. So when we need to go, we need to go to moles because we want moles per liter. So we need to convert from grams to moles using our molar mass, mm. So our molar mass is 154.996 grams per mole. Note the way that I want to write it. I write it with grams on the bottom so that I can cancel out grams. That gives us moles. And then to get to moles per liter, we're going to divide that number of moles by our volume. So our volume is 250 milliliters. But we want it in liters, so I'm going to move my decimal place over 3 times. That is the same as what will happen if you plug it into your calculator and divide by 1,000, or plug it into your calculator and multiply by 10 to the minus third, which is the definition of milli for you guys. So we would put that down here. 250 milliliters is 0.250 liters, and there's nothing really here, so I'm just going to put a 1 up there. If we multiply straight across the top, there's nothing to multiply across the top, so I'm just going to take 22.5 and divide it by 154.996 and divide that by 0.25. So you want to use the division sign twice, or you want to put 154.996 times 0.25 in parentheses when you divide by it, because if you just put in 22.5 divided by 154.996 times 0.25, I know what you mean, but your calculator doesn't. So you have to use parentheses to help out your calculator. So I ended up with 0.581. I had 3 sig figs on my things that I started with, so I'm going to end up with 3 sig figs. So this is 0.581 molar, or moles per liter, same difference. So this is our concentration of cobalt sulfate. And if we want to find out what the concentration of the ions is, we want to write out our equation for the dissociation. So this is soluble because we just made a solution out of it, so we know that it's soluble. So it is an ionic compound that is soluble, so it dissociates 100% in solution, and we end up with cobalt 2+ and sulfate 2-. There are no subscripts, so we don't have more than one of either of these things. So it's a 1-to-1 dissociation for both ions. So the concentration is the same for both ions and the solution. So unlike our calcium chloride example, this one does match up. All right, so that's it. Sorry that was so long. I'll see you tomorrow in class. Have a good night.